All right, folks, and welcome back to our discussion of factorial ANOVAs. This video is going to be an important one. It's a concept that sometimes people have a little bit of trouble with, but it's a really key one to understanding how factorial ANOVAs work and what they can tell us. We're going to be talking about what are called main effects and interactions. Now, most folks usually get main effects reasonably well, but the interactions tend to be a little trickier. We got an interaction example on the board behind me here, but let's not worry about that for just a moment. Let's talk about some basic ideas. So remember that our factorial ANOVAs, as I've mentioned, actually are multiple hypothesis tests folded into one. There are multiple effects that you might be interested in understanding. All of those effects involve calculating and comparing variance. And here's the point where I'm going to tell you, be mildly grateful, however miserable this course is for you or whatever, because when I took this class, we had to calculate factorial ANOVAs and all their many, many underlying hypothesis tests by hand. And we had to do it up to 3 or sometimes 4 factors. It took a long time. You wind up calculating a lot of sums of squares. But again, these are analyses of variance. We're just going to talk about them conceptually. They involve calculating an F ratio for each of the hypotheses that we're testing. So again, a design with multiple factors has multiple possible effects. Here's what we test for. We test first for what are called main effects. The main effect is the isolated independent effect of each individual factor on our DV scores. There's one possible main effect for each factor. There's an F ratio for each main effect. It may or may not be significant, but it works the same way as the F ratios in our one-way ANOVA. So, for example, let's take our study design where we manipulated what movie people watch and we manipulated whether they were provoked or not, 2 separate IVs. Now, we could see a main effect for movie type. For a main effect for movie type, that suggests that the type of movie people watch independently affects aggression, meaning regardless of whether they were provoked or praised, just across the board, people that watch certain kinds of movies were more aggressive than people who watched others. So for example, you might find people are more aggressive after watching violent movies compared to the other movie conditions, but just across the board. It doesn't matter if they're provoked or not. The people that watch the violent movie are always more aggressive on average. So that'd be a main effect for movie type. It doesn't matter what's going on with the other factor, the other IV, just independently, this IV predicts DV scores. There are significant differences between conditions on just this IV by itself. We also would calculate a main effect for the second factor, provocation, in this case. So provocation might also independently affect aggression, meaning people are more aggressive after being provoked no matter what movie they watch. They're just always higher in aggression when they've been provoked than when they've been praised. So that's an independent, isolated effect for provocation. It doesn't matter what movie you watched. If you're provoked, you're more aggressive than if you're praised. So these are 2 separate main effects, one for the type of movie, one for provocation. Each one would get its own F ratio and its own hypothesis test, which may or may not be significant. So you've seen main effects before, actually, in the one-way ANOVA. The one-way ANOVA, that F test that you ran, that was just a main effect for the single IV or quasi-IV in that one-way ANOVA. Again, a multi-IV design has one main effect for each of your factors. It also could potentially have what's called an interaction. Okay? Now make sure, again, you pay close attention to this part because interactions are really important and people oftentimes struggle to understand them, especially early. Here's what it means to say that 2 factors interact. It means that the influence of one factor on the DV is altered by the level of the other factor. In other words, it's not a consistent effect across the board. How the first factor affects DV scores is greatly influenced by the level of the second factor. So, for example, we mentioned an antidepressant study in the last video. The effect of what antidepressant you're taking, what condition you're in, it might change based on that second factor, based on whether it's described as highly or moderately effective. Maybe there's only a small difference between antidepressants and placebos when it's described as moderately effective, but when it's described as highly effective, that difference spreads out. It gets a lot bigger. There's a much bigger advantage for antidepressant than relative to placebo when they think it's highly effective. That would add nuance to antidepressant treatments. That would tell you that in addition to just giving people the right medication, you also need to develop positive expectations that it's going to work. Because again, You're seeing that it's not just about what substance they're taking, what pill they're taking, it's also about that expectation, if they expect it to be highly or moderately effective. Our other example, we talked about just measuring two quasi-IVs, political affiliation and gender, and just measuring their approval ratings of the president. So different political parties' ratings of that president might differ by gender. Maybe, generally Republicans feel more positively about a Republican president than Democrats, so there's that overall difference there, but maybe that effect is a lot weaker for women than it is for men, for example. So that's a case where you would see an interaction between the two. So interactions mean the influence of one factor is dependent or altered by the level of the other factor. Here's the way I was always taught to be able to recognize interactions, because we can think intuitively in terms of interactions. We really have seen this sort of concept before. You probably just haven't heard it called this. If to explain the effect of one factor, you have to say it depends and then cite the other factor, that is, you probably are describing an interaction. So let's take our movie clip example. We have a chart here of our movie clips, and we're just going to eliminate the drama condition just for simplicity's sake. We're just going to talk about violent movies versus comedies. Now let's say that you got a pattern of data that looks like this. And here's people who are praised, here's people that are provoked, and this represents their level of aggression. So somebody said, hey, what effect does what sort of movie you watch have on people's aggression? You have to say, well, it depends. When you are praised or not provoked, it doesn't really matter if you watch a violent movie or a comedy. There's not a big difference in aggression level there. But if you are provoked, those options spread out. Provocation has a much bigger effect on people who have watched the violent movie than it does on people who have watched the comedy. So the difference between those two conditions, again, gets much larger there. So does movie clip influence aggression? It depends. If there's no provocation, not really. If there is provocation, yes, it matters a lot. The people that watch violent movies are more aggressive than people that watch comedies. So that's that idea of an interaction. The effect of what movie people watched is altered by that second factor of provocation. So let's take a point of emphasis here on main effects and interactions. Again, keep in mind that we're still just calculating F ratios, and again, also keep in mind you're not actually going to have to calculate these. You're just going to have to show an understanding of how they work. It's that same F ratio just conducted several times. You get one hypothesis test, one F ratio for the influence of each factor by itself. Those are the main effects. There's one main effect for each factor. You get one F ratio, one possibly significant result for the combination of factors, whether one factor is altered by the level of the other factor. So its influence isn't direct, it is altered based on the level of that other factor. Each one's a separate test. Any combination can be significant or non-significant. All main effects and interactions could all be significant at the same time. They could all be non-significant at the same time. Or there could be, one or two of them perhaps as significant and the rest are not. All of those are possible. They all are independent tests. Main effects and interactions give us nuance when we have these complex research situations with multiple factors. We can figure out what's really happening in terms of those factors altering DV scores. So let's take another quick example. Let's say that we are manipulating how much caffeine people consume and the room temperature that they take and examine, and our DV is test performance. So participants consume either, let's say, a decaffeinated cup of coffee or a regular cup of coffee, then they take a test in a hot room, let's say like an 80-degree room, or a normal temperature room, let's say 70 degrees. So let's break down this design first. We have two IVs, caffeine consumption and temperature, and each one has two levels. We have one DV, which is test performance. If I describe this to you on an exam, you should be able to figure out, hey, this requires a factorial ANOVA because there are two factors, two IVs being manipulated, and it's a between participants design. So our factorial ANOVA, when we ran this ANOVA, we would test for a main effect of caffeine. We would test separately for a main effect of temperature on test performance, and we would test what's called a caffeine by temperature interaction, whether or not those two factors seem to interact with each other. Our notation for this design would also be a 2x2, and again there are two terms because there are two IVs. Each one has two conditions, so your actual numbers are 2 and 2. And there will be 4 total cells here. We're going to see what those cells look like in just a second. If you added an extra condition where, say, there was no drink at all, your notation would be 3 by 2 or a 2 by 3 or 6 cells. So here's a chart. Let's say we run this study and we get some data and we lay out our data like this. First of all, notice they're called cells like in kind of a biology setting or prison setting. It's a boxed in area that contains just the combination of scores for the combination of factors. So for example, this cell represents people that had a caffeinated drink and were in a hot room. This cell is people that did not have a caffeinated drink and were also in a hot room. And again, notice we have 4 different cells here, 4 different combinations of factors, and we have the average score, the cell mean, for each group. Take a second and eyeball this. You should already be able to pick out some trends in the data set overall, what sort of things seem to be influencing test performance. Give a little bit of thought to that. Pause the video if you need to. But overall, the first thing we do in a factorial ANOVA is look at our main effect. So let's look conceptually what a main effect would look like. Let's say we just wanted to look at the main effect for caffeine. If that's the case, we want to disregard what temperature the room is and only look at whether they had caffeine or not. So how could we do that? Well, we could average these cells together. If we average the people together who had caffeine and the people who didn't and compare them, we'd find the average test score for caffeinated folks is 81.5 and for decaf folks is 83.5. Not a big difference there. People that didn't have caffeine did a little better. Is it statistically significant? We would need to conduct an F test to figure that out. But the point is, at this stage, that's what the main effect would be, just comparing our caffeine drinkers to our no caffeine drinkers. Then we might look at room temperature by itself. We ignore whether people had caffeine or not. We just average the people in the hot room and the people in the normal room. The average of people in the hot room was 76.5 on that exam, and in the normal room, 88.5. That's a big difference, a 12-point jump in your scores if you take the test in an 88 or in a normal temperature room compared to a hot room. That very likely is a main effect, though again, we would need an F test to be sure. But that looks like there's probably a main effect there. The interaction is a little trickier, but if you're eyeballing this, you could probably figure out some ways in which the effect of one IV depends on the effect on the level of the other. So what's the effect of caffeine on test performance? Okay, we saw in a main effect that they were pretty close together, but when we look at it in the context of both factors, we have to say it depends. Well, taking caffeine actually is better in a normal temperature room. People's scores went up, but they were much worse in a normal temperature room. So if the room is hot, you want caffeine consumption. You don't want caffeine consumption, excuse me. In a hot room, caffeine consumption impairs performance. In a normal temperature room, it helps. So there's that it depends. There isn't a consistent effect there. Caffeine is good for your test scores in a normal temperature room. It's bad in a hot room. Or you can flip it and say, what's the effect of room temperature on test performance? Even though there's probably a main effect for room temperature, we can still say it depends on caffeine consumption. Hot rooms are worse across the board, but they are far, far more detrimental for caffeine drinkers. A 19-point drop there when going from the normal to the hot room, only a 5-point drop when looking at the folks that did not drink caffeine. So a pretty common way of recognizing interactions is the sort of thing I did up there, creating a line graph and looking at whether or not those lines are parallel. So here's a chart of that exact same data. These are all the same numbers. They haven't changed. Here is our normal temperature room. Here is our hot room. Notice that caffeine works very differently in a hot versus a normal temperature room. It's bad in a hot room. You want to have no caffeine in that room to do your best in that hot room. But it's good in a normal temperature room. You would want to have caffeine in a normal temperature room. It seems to improve people's scores a little bit there. Notice those lines are not parallel. That is an indication of a possible interaction. We would still need to conduct an F ratio, but we're not even worrying about those calculations. We're worrying about conceptually understanding what a main effect is, what an interaction is, and this idea that you can kind of visualize interactions by creating these little line graphs and seeing if the lines are parallel. But we're not even going to worry about the significance testing part of that, except to say that you would conduct those significance tests. All right, that is the end of the main effect and interaction. Again, if you're having trouble, continue reviewing the test material, go through this lecture, try to think of everyday examples of interactions. We are going to close out the module and the unit by next talking about post hoc tests and situations where you have 3 or more factors. Uh-oh.